So we'll continue on talking, obviously, about what we've been talking about. We sort of completed last time, though, talking about buffers. Again, a reminder, a couple important points about a buffer. A buffer is, again, a combination of either a sort of weak acid and its conjugate base, or really you can make it as a weak base and its conjugate acid. A reminder that we really can't have a buffer that is made up of a strong acid or strong base. And again, the reason for that is a strong acid or strong base will pretty much not set up an equilibrium. And the downfall of it not setting up an equilibrium is in order for a buffer really to work correctly, you do need both the acid part of the buffer and the base part of the buffer really in the solution at the same time. So again, both of those things, the weak acid, the conjugate base, or the weak base, conjugate acid, they're both in that solution depending on how you made your buffer to begin with, which gives the buffer its ability, as we talked about, really to prevent the formation of more free H plus or OH minus. And really, again, as we've talked about, that's essentially how a buffer works, is it really does prevent that formation of those free H pluses or OH minuses, depending on sort of what you're doing. And because of that, it essentially keeps the H plus concentration relatively constant. And because the H plus concentration really doesn't change all that much, even if you add acid or base to it, we will have a relatively constant pH. The other important thing is, some of the things that we sort of saw in the lab on Monday and stuff like that is, you can make a buffer from a reaction of a, say, strong acid and, say, a conjugate base. So, for example, like the one in maybe part B there, we had hydrochloric acid that was being added to sodium acetate, which was our basic part of the buffer. And again, we would make our acetic acid plus our sodium chloride here. The important part of this, though, is, again, if you went through sort of the moles part of all these guys, the change part, we would lose all of the moles of our HCl in this particular case. And we would end up with 0 for this guy. We would end up with some moles of this guy and some moles of this guy. So the reaction itself is not the buffer. The buffer is actually made as a result of the reaction being over. So the end result of the reaction happening is that formation of that buffer. And it's sometimes referred to as making a buffer in vitro, which is basically in the test tube or sort of in the beaker. You can make that buffer as a result of a chemical reaction. But again, even though HCl plays a part in making the buffer, the definition of the buffer itself is what is left over at the end of that reaction. And the same thing happened when you took some sodium hydroxide plus the acetic acid in, say, the first one. When we did that, we made some sodium acetate and some, what do we got there? Some water. Now, again, even though we started with some sodium hydroxide, by the time the reaction is done at equilibrium, it's basically zeroed out. And what we're left with, again, is acetic acid and sodium acetate. Again, it is this part at the end of that reaction that is a buffer. So again, sometimes people, I get a little confused on that aspect of it. You can absolutely sort of make a buffer in like a test tube, in a beaker, whatever it may be, through a chemical reaction. but the buffer itself is not containing at that point a strong acid or strong base, even though you kind of used it to make the buffer. You know, it's pretty much all used up to make the buffer, and you have none of it left over. So again, that's why when we talk about the definition of a buffer, it cannot contain a strong acid or strong base, because really it's not able to really set up that equilibrium. But you definitely can, as we saw sort of in experiment 6, we might see in experiment 7 as well. And we'll see a little bit today that you actually can form a buffer. And again, the buffer is the ending part of that reaction. Any questions on sort of that stuff we talked about before? Okay, so we're now going to talk then about the next really big topic, which is titrations. So hopefully maybe have done titrations before or seen titrations before, but just in general, a titration is typically a process that we use to a lot of times figure out, for example, the concentration of an unknown substance using a known substance. And usually the components of sort of a titration or the equipment that we obviously use, a lot of times we use a burette, which is very badly drawn here, much better picture down there. But a burette is, you know, a big long glass cylinder. It usually has what is referred to as a stopcock right there, and that's basically the on-off switch. Usually when we do sort of a titration, you got a beaker or a flask underneath it. And what we're talking about here, sort of in this experiment, is sort of acid-base titrations. So for example, you could fill your burette with the base, could fill your beaker or flask with the acid. And we typically, in addition to the acid, also throw in there an indicator. And basically, we slowly sort of add the base, in this case, to the acid. And we're really going to get, in this case, obviously, an acid-base reaction that's going to occur, where we'll make, obviously, water and some salt happening. And as we do this, usually we use the indicator to allow us to know when we've reached what is referred to as the equivalence point. And the equivalence point, you know, in an acid-base titration is the point where the reaction is really complete. But usually in a acid-base titration at the equivalence point, that is the point where we've reached exactly the moles of the acid will equal the moles of the base. So it's that point where we've perfectly hit adding exactly the right amount, in this case of my drawing, base to the acid to completely neutralize all of the acid moles that we started with. And that's basically the equivalence point. That usually accompanied by some type of change in color. Hopefully, if you've done a titration, you don't get a red one like this, I imagine. But you might, depending on the indicator. But, you know, you see that change of color. And again, that should indicate to you that you should probably lay up the titration at that point and stop. Not to be confused with sometimes another sort of terminology that we hear in titration, which is the end point of a titration. The end point of a titration is pretty much what it sounds like, is pretty much when you stop your titration. And if you do a good titration, hopefully your end point and your equivalence point is essentially pretty close to each other. So hopefully you're stopping at the right point. And again, a lot of times in a traditional sort of titration, we're really interested in, you know, stopping at that equivalence point, and we hit that color change. A very common indicator that's used, for example, is something like phenolphthalein. And phenolphthalein is probably one maybe that you've used before. If you've done a titration, it is, you know, colorless in acidic solutions. It's actually colorless in neutral solutions. And it turns everybody's favorite color, which is pink in basic solution. Hence over here, you can maybe see the tinge of pink in that flask there when they reach the equivalence point. If you ever used phenolphthalein or done an acid-base titration, you probably have used phenolphthalein, and you've also probably been yelled at, make sure you stop your titration at the very first sign of pink, especially if you're using phenolphthalein. Obviously, the color would be different if you're using something else. So faint of a color of pink, usually when we use phenolphthalein, that you got to put like a kind of white piece of paper under it or a paper towel to kind of even see the pink color. And the reason for that is, as we will talk about here as we continue, is really indicators. Indicators actually work over a pH range. So they actually work over a specific pH range. And for example, something like phenolphthalein works something like a pH of 8.3 to like a pH of 10-ish. At 8.3 is kind of colorless. As you go this way towards a pH of 10, gets your super dark pink at that point. And somewhere in this range is like you could barely see a tinge of pink to indicate that you should stop the titration at that point. We'll also talk about if perhaps you've done a titration before. You might have always hear the very common phrase when people do titrations is, I only added 1 drop and the thing went from like no color to like super dark pink, which is, my favorite color when I'm titrating. Just make it super dark pink and hope for the best there. We're going to explain really why that happens. So that's a very common thing. Again, if you've ever sort of physically done a titration, which I think they used to do in Chem 3 as well, and Chem 1A, you do it as well. So if you've ever done one before, that's a very, very common thing. And it does happen. You could literally just add like 1 little drop and the thing goes from like no color to like, I'll go extreme red here to our super dark pink and stuff like that. So we'll explain really why that happens when we do a titration. But a lot of times when we do get to the equivalence point, we could use some basic stoichiometry to figure out things like perhaps the concentration of an acid. So this was like an unknown acid and we weren't really sure what was going on in terms of its molarity. And we wanted to figure out the molarity. And we knew that we started with like 25 milliliters of it. And to reach the equivalence point, we would know something about the base. So maybe it was 4 molar, and it took 35 milliliters to reach the equivalence point. We basically could do a stoichiometry problem between these two, basically to figure out the molarity of the unknown acid, because we would know something about the base. So we could take the volume of the base. I'll just make it in liters. The volume of the base times the molarity of the base would give you the moles of the base. And then based on your equation, your balanced equation, if it's a 1-to-1 relationship, for example, you can then go from moles of your base to moles of your acid using stoichiometry. And this, again, is something you probably have done calculations before, moles of acid. And then obviously, since you know the volume of the acid you use, at that point, you could divide by the liters of the acid and you get the molarity of your acid. So in a titration, we really do know sort of all the information usually about one component, either what's in the burette that we're adding, or maybe what's in the beaker. And we use really stoichiometry and solution stoichiometry to figure out, basically what is happening in terms of concentration of that unknown substance. Any questions on that there? By the way, you see a water bottle there, and that's because a wash bottle, you could add pretty much as much water as you want in the titration, as long as you don't go super crazy. But the amount of water really will have no effect on sort of what's happening in the reaction. So sometimes you need to add more water and it doesn't really matter. Also, sometimes if you've ever done a titration before in person and you see as you're sort of titrating, what you typically will see as you drop those things in is, the color will stay a little bit and then it'll go away. And then the color will come back as you drop some more and then kind of go away. And you'll kind of see the color every time you're dropping kind of stay longer and longer before it sort of disappears. And when you're getting really close to the equivalence point, one technique that's very commonly done is what's sometimes referred to as adding a half a drop. And that's basically you get a drop of what you're adding to kind of form on the end of the burette. You take your wash bottle and you basically wash it down. And that basically will dilute that drop. And sometimes that's enough to get you to that really light color of pink that you're looking for. Again, especially if you're using phenolphthalein, versus if you did sort of a full strength drop, that might be too much and really get you too far away and that really, really dark sort of pink color. Any questions on titrations there? All right, so we're going to actually talk about 3 different types of titrations. And we're actually going to be looking mainly in this class about what is happening throughout the entire titration. And we're going to be interested in sort of what is happening in terms of the pH of that solution as we continuously sort of add solution to it. What we're looking at is a typical titration curve. And on this titration curve, typically what we see is on the Y, we have our pH. On the X here, in this particular case, this is the volume of the base that we're adding. So this would be like a titration, something like we're adding a strong acid and strong base. So we take something like hydrochloric acid plus some sodium hydroxide, which is obviously a strong acid, plus a strong base. That will give us some water and our sodium chloride. And just so you have sort of a visual representation of where everybody is, in this titration, basically up in the burette is our sodium hydroxide. And we are adding that to a beaker, a flask that contains HCl. So we're basically adding our sodium hydroxide, in this case, to our hydrochloric acid. A titration curve, as you can see, basically shows you how the pH is changing as you continuously drop, obviously in this case, the sodium hydroxide in that solution. So let's talk about how we can sort of figure out, what is going on in each of the places along here in terms of this curve. So let's talk about what happens at the very beginning here, the very start of the titration. So at the very start of the titration, before we add any sodium hydroxide, let's think about sort of, what we have. So what we really have kind of floating around in that solution is really hydrochloric acid. That's all we have in there. So if we wanted the pH of that solution, because hydrochloric acid is a strong acid, we know that it will 100% break apart into H plus and Cl minus, which means at this point, we really just need to figure out the H plus concentration in that solution. So for example, if we started with, say, 25 milliliters of a 0.1 molar hydrochloric acid solution, because we haven't added any sodium hydroxide in this case, that is going to be the concentration of our hydrochloric acid, which means if we want the pH, because this guy is 0.1 molar, it's a 1-to-1 relationship between that and H plus, it will also be 0.1 molar, which means we could very simply figure out our starting pH by going right into our pH equation. Again, no volume being added, so we don't have to worry about any of that. And we will end up with a starting pH of about 1 in terms of where this titration is starting. So if we look back here on the chart at volume 0, we do see 1 in terms of the pH. Sorry about that. Any questions on that so far? And again, we're not adding volume at this point, so we don't have to worry about doing things in moles or anything like that. We could just take the starting amount in terms of its concentration. So then let's talk about what happens on this titration curve as we decide to actually start adding some sodium hydroxide. So basically, at the start here, we're going to add sodium hydroxide. We see the pH kind of going up, and all the way to before number 2 here, is number 1, before we reach that equivalence point. So when we do start adding the sodium hydroxide, this will be like number 1 here. Number 2, when we start adding sodium hydroxide, we are definitely adding volume, right? So we are adding volume here, which means that we do need to do an ice table because there is going to be a chemical reaction that's going to occur. And we also need to do that ice table in terms of moles because, again, we are adding volume, which means the molarity will change. But again, the moles will not change. So what happens in this particular case is we will get the reaction. So we'll have our hydrochloric acid. We then will add our sodium hydroxide to it. And it will make water and our sodium chloride in this particular case. We would want to do this in terms of moles. So just for purposes here, I'm going to say that I'm starting with 4 moles of my HCl. And again, I just made up that number. So I'm just going to say I made up that number. Made up. Yeah. So I'm starting with 4 moles in this case. We'll use this guy here. 4 moles of my HCl. I know I'm before the equivalence point in this case. Right. And why being before the equivalence point is important is when I'm at the equivalence point, I know the moles of my acid should equal the moles of my base. So since I am adding sodium hydroxide, I should definitely have less moles of sodium hydroxide than HCl, again, because I'm before that equivalence point, which means at this point, I have not added enough sodium hydroxide to use up all the moles of my hydrochloric acid. This would be 0. This would be 0. Now, what happens with the change part? Well, because I have not reached that equivalence point at this point, and I know that I have less moles of my sodium hydroxide than I do my hydrochloric acid that I started with, the sodium hydroxide in this case is like the limiting reagent, which means it's pretty much going to get used up. So we will actually use a number here, which in this case would be the moles of the sodium hydroxide. That means when I reach equilibrium, I would have 2 moles of this guy, I would have none of this guy, and I would have 2 moles of this guy. So very much like what we talked about with the buffers here, because we are adding volume, we definitely want to do this first ice table in terms of moles. And what we want to do is also what we talked about with buffers is as soon as you're sort of done with this first ice table, it's a good idea to convert everybody back into molarity. So how would we convert it back into molarity at this point? We would need to figure out what the total volume is. So to convert everybody back to molarity, we would want to divide by the liters, which is the total volume at this point, and divide this guy by liters to get everybody back to molarity. Again, in this case, just so we're clear, the total volume would be how much you added from the burette, and obviously how much you started with in like your beaker or your flask, whatever it may be. So that, again, that's how you would obviously get the total volume at this point in the titration. So again, if you're not really sure what's happening at this point, you could use your ice table to kind of figure out how we could figure out the pH. So what we're left with at this point is hydrochloric acid, and we are left with sodium chloride. So this is where all the stuff that we've talked about, it's important to keep in mind, because hopefully when you see that sort of combination, first off, you will remember that this sodium chloride is a neutral salt, which means it is not going to affect the pH, which means even though I got numbers, I'm not going to use that buffer equation like I might want to because I got two numbers, but it's really not going to affect the pH. The other thing that, again, you should realize is what we are really left with at this point is the hydrochloric acid, which is a strong acid, which means we now can figure out the H plus concentration from here. And that would obviously get us into the pH. Any questions on once you start your titration, and this goes all the way up until you reach that equivalence point, you need to do at least one ice table. That ice table does need to be done in moles because we are adding volume. And the purpose of the ice table is to figure out what is the new concentration of our strong acid. And because it's a strong acid, what that will also mean is you will then have the H plus concentration, and that will allow you obviously to go right into the pH equation and calculate the pH of that solution at that point. Any questions on any part of that there?
Could you explain again what happened to the sodium chloride?
Yeah, so really at this point in the titration, wherever you kind of stop the titration, when you open it up and shut the burette, you've added that sodium hydroxide in, it's going to react. And really at this point, you predominantly have a couple of things kind of floating around in that solution. You have the HCl, which is basically going to be your H plus floating around and your Cl minus. You also have your sodium chloride floating around, which is going to be sodium ions and chloride ions. So when we look at the sodium chloride part, like we talked about with salts and hydrolysis, sodium is group 1. So if you remember, any guy that comes from group 1 or group 2 probably is going to be from a strong base, which means the sodium will be relatively weak and considered neutral. So it's not going to affect the pH. The Cl minus, obviously, as we can see here, came from hydrochloric acid. Hydrochloric acid is a strong acid, which means the Cl minus is its conjugate base, which will be relatively weak. So if you remember, it has those opposite sort of relationships. If something comes from a strong acid or strong base, its conjugate partner will be relatively weak. And really what that means is it will not go through hydrolysis or have any effect on the pH, and it's basically considered a neutral salt. So even though technically if you did your ice table, you would definitely end up with a number here. And sometimes people want to go into that Henderson-Hasselbalch equation because you got two numbers. But in this particular case, because it is sodium chloride, it's really not going to have any effect on the pH. It's just going to be neutral, basically a pH of 7. So it is definitely still floating in there, but it won't have any effect on the pH. So really the only thing you're left with at this point is that hydrochloric acid that's really supplying a lot of that H plus, or the predominant amount of H plus in that solution. And that's why it then becomes sort of just a strong acid sort of pH calculation at this point. The purpose of the ice table is really to figure out what is that new concentration of your strong acid at this point. Other questions on that? Okay, so again, this is basically the type of calculation that you would do again from when you drop that very first drop all the way until you reach the equivalence point. So if we go back and sort of look at our graph here, we do see, as I mentioned here, pretty much as soon as you drop it, we do start to see the pH going, and this is this classic sort of S curve that's happening. And what we do see is we're approaching the equivalence point here. And what we see as we approach the equivalence point in a titration, and this is commonly seen when we look at titration curves, we typically have this sort of S curve that sort of happens, equivalence point, here somewhere. We essentially go pretty vertical. So what does that mean? Well, what does that means is as we're doing a titration, we typically will kind of see at some point a pretty big jump in pH to the equivalence point. Then we'll actually see another big jump past the equivalence point until it kind of levels off on top. And this effect that we see as we approach the equivalence point, where it goes pretty vertical, is the reason why you sometimes will hear people say, I just added one drop and the thing went super pink. And the reason for that is, if you remember, as I talked about before, an indicator like phenolphthalein, for example, works on a pH range of like 8.3 to like 10ish. And again, at the 8.3, it's really colorless. But here it's super dark pink and obviously very light pink in this region and so forth. So the point here is, as we go to the equivalence point and we go pretty vertical, what does that mean in terms of volume that we're adding? So what that means is, if you look here and you look at the equivalence point, and as you approach the equivalence point, you're going pretty vertical, which means you are not adding a lot of volume, but you are definitely changing the pH a lot, right? The pH gets changed a lot. So that's why when you do this and you have done the titration maybe before and you go, I just added one drop, there was like no color, but I added that one little drop and then the thing went super dark pink. We're always seeing that's pink. And that's because even though you added one drop, which is not a lot of volume, as you get close to that equivalence point, that may be enough to make the pH go from like here, like up to here, right? And what that's going to look like when you're visually look like it is, you started like over here in the colorless range, you add that one drop, you just jump way over here to that dark pink range. And that's why you see that really big change in the color, even though if you were really careful and you only added one drop, you're really still close to the equivalence point. Any questions on why you kind of see that big change that sometimes occurs when people do it? Also, yeah, go ahead.
If the relationship between the HCl and the base is kind of like a 1-for-1, you add some OH and it gobbles up a proton and turns into water. How come when you reach near the equivalence point, the pH relationship is so like exponential? Just a little bit of OH skyrockets the pH.
Yeah, so typically when you're doing that sort of a titration, you're adding that sodium hydroxide, so you're continuously chewing up the H plus that was there, right? You don't usually restock it as you're doing the titration, right? So you're just continuously adding, right? So even though we sort of look at each of these spots as like independent of each other and stuff like that, but in the real sort of situation, you're continuously dropping drops, right? Which means you're continuously eating up, right, this HCl or the H plus that's available. So as you're growing to that sort of equivalence point, you have a much smaller amount of H plus than you started with way back over here, right? So it doesn't take as much at this point to kind of tip it over the edge, if you will, and make that kind of big jump in terms of pH, because at this point, you got a minimal amount of H plus because you're getting to a point where the moles of the H plus, or the acid in this case, right, is going to equal the moles of the base. So as you're continuously doing this, you're basically continuously eating this up, eating this up, eating this up. And, you're bringing down your H plus concentration. You're kind of also bringing up your OH minus concentration until they kind of hit each other. And it's that point when they kind of hit each other, get near each other, that, you're kind of tipping the scales a little bit more in the basic range by adding that kind of constantly. So that's why you typically do see this kind of big sort of leap that occurs when you get there. It's just a product of you're kind of chewing this up. Some of this is going to be chewed up by the native stuff that's floating around in there as well. So you get almost this imbalance that happens where you kind of almost equal, then you kind of tip a little bit too far. And that's why, again, do see that sort of big jump in pH as we reach there.
Okay, thanks.
You're welcome. And that's why if you look at just the curve here at the very outset, there's not a very giant change in pH happening, right? And that's because, you got a relatively good amount of H plus at this point. But as you continue, it's getting smaller and you're just continuously supplying that OH minus. So it's kind of like a balancing act until, you get to that point where you just need a little bit of it to kind of go over the hill, kind of like the big ball on the top, right? You just need just a little nudge at some point to make it kind of fall over. And that's sort of what you see. Other questions? Okay. So when we do kind of come up here vertically, like I was mentioning, because we're not adding a lot of volume, but we are changing the pH a lot, that's why, we do see that very big change in color. And that's why people usually will yell at you, hey, be very, very careful. We want the lightest color of pink that you could get, especially using phenolphthalein, obviously. You could barely see it. And because of that, it'll hopefully kind of keep you near where the equivalence point is and sort of in this range. The truth be told, though, is if you just kind of were very careful and you missed it by 1 drop or 2 drops, even though your pH is way up here, your volume is probably pretty close anyways to the equivalence point. That's why I don't know if you've ever done it in person and you've had an instructor, they might have told you, oh, that's too pink, go back and do it again. You really didn't need to, because the volume you would have ended up with is probably pretty close to the correct volume. And again, that's assuming that you weren't crazy and titrated like me and just opened the thing up and let everything drop in there until it went super dark pink and you did really jump way past in terms of volume. And that's why you have to be careful. But if you're really careful, sort of as you approach the equivalence point, did kind of drop by drop by drop sort of situation, and again, you missed it by like 1 drop or something like that, you probably didn't need to dump it. If they made you dump it, you could have just been all right in terms of that. But if you really weren't being very careful and you just open this thing up and just let it just not really drop and just go, and then at some point you shut it and you're like, oh, cool, I'm at dark pink. You really don't know where you're at. You could be like dark pink over here. It could be dark pink over here, or you might be lucky and be dark pink very close to the equivalence point volume. And so that's why they usually tell you to be kind of go fast at the beginning and then really kind of slow it up as you kind of get to the equivalence point. So you could really dial in, where that equivalence point sort of is. But in most applications, people are usually fairly careful. And if you are fairly careful, you miss it by 1 or 2 drops, you really don't have to restart it and do it again. You probably would have been okay in the calculation. Again, if you weren't careful, though, you could have really overshot it and ended up way over here. There's really no distinction in that pink color, in this range, if you're using phenolphthalein between the two. Any questions on that there? All right, now that I scribbled all over this thing, let's talk about actually calculation-wise what is happening when we do reach the equivalence point. So let's talk about, when we're here actually at the equivalence point, we'll call it right there, number 3, sort of what is happening in terms of the calculation at that point. So we'll go here to like number 3, which is at the equivalence point. So at the equivalence point, we would obviously have that reaction of our hydrochloric acid in this case, plus our sodium hydroxide. Again, giving us our same reaction that we've been dealing with here in this titration, our sodium chloride. Now, again, I'm just going to make up the number and say that we started with 4 moles here. And again, we would want to do this in moles because we're still adding. And again, just made up that number. Because we're at the equivalence point, what we should know is at this point, the moles of the acid should equal the moles of the base, which means the sodium hydroxide moles I should have is 4 moles. It should be exactly the same. This would be 0. That means at this point, you can't mess up. There's only one number to choose. It's got to be 4 in this case. That means when we do reach the equilibrium after we added it at the equivalence point, we would be left with 4 moles of our sodium chloride, which obviously we then could convert back to molarity by dividing by the total volume. So what are we left with at the equivalence point in this type of titration is we are left with sodium chloride. So just like the earlier question was, and we talked about, the sodium chloride here is still a neutral salt, which basically means there is no calculation. You would expect the pH in this type of titration at the equivalence point to really be a pH of 7. And that's really why in this strong acid, strong base reaction, they're sometimes called acid-base neutralization reactions, because if we do take something like our hydrochloric acid and our sodium hydroxide, and we go through and look really what is happening here by writing a total ionic equation, which is H plus Cl minus plus some sodium ions plus some hydroxide ions. Water would stay together because it's a pure liquid. Anything that's solid, liquid, or gas stays together. Weak electrolytes as well. We end up with this guy. And perhaps you remember from total ionic equations, there are certain ions on both sides which look exactly the same, which would be these guys. These are our spectator ions, right? They're just there watching what's going on. These guys cancel out. And what we're left with is really the overall reaction whenever we take a strong acid and a strong base together. It really is the H plus from the acid coming together with the OH minus from the base to form our good friend water. And again, Y is sometimes referred to as a acid-base neutralization reaction. Also why when we hit exactly that equivalence point, we would expect it to be a pH of 7. So any titration involves pretty much a strong acid and strong base. Once you reach that equivalence point, you should be left with always a neutral salt, which won't go through hydrolysis. And we would again expect it always to be at a pH of 7. Question on what's happening at the equivalence point here. And that's what we see here after I scribbled on it. But if you look over here, you can see again at the equivalence point, we have a pH of 7 here on the actual chart. Now, probably in your experience, if you have some experience in titrations, that's usually where you lay up the titration and you stop. But, you know, perhaps you don't want to stop there and you want the full titration curve. So let's talk about what happens when you see that pink color, for example. It does not deter you. You say, that's a nice color, but let's see how pink we could get it, which oftentimes happens when you do titrations because you got some, you know, sodium hydroxide in there and just let it go. So what happens when we actually do pass the equivalence point, all the way past it until when you decide to finally lay it up and stop? So we'll call that number 4 in this titration part. What happens when we actually go beyond the equivalence point? So when we go beyond the equivalence point, and we'll call that number 4 there, past the equivalence point. And again, maybe you just think, you know, that indicator is just a recommendation to stop. So you decide to continue past the equivalence point. We are also going to obviously still have our same reaction happening here. And again, since we are still adding, obviously, volume, we're going to be doing things in terms of moles. So initially, I'm going to again use my made up number of 4 moles that we started with. In terms of our added amount of sodium hydroxide, since we are past the equivalence point, we should know that the moles of the sodium hydroxide that we are adding should actually be more than the moles of the HCl that we started with. So I'm again just going to make up a number and say we have 6 moles here. Again, this should be more at this point, because remember when we are at the equivalence point at number 3 step here, the moles of the acid equals the moles of the base, which means when we go past it, and because we're adding base, the moles of the base should end up being more than the moles of the acid when we get to the fourth spot here in the titration curve, because that's what we're essentially adding as we're doing the titration. What does that really affect? Well, it really affects the idea of, if you remember, before we reach the equivalence point, the moles of the sodium hydroxide were the limiting reagent and the HCl was the excess reagent. There's actually a switch that occurs in this point. Now we got plenty of sodium hydroxide. It actually becomes like the excess reagent, and the HCl becomes like the limiting reagent, which means the change part here is actually going to be the HCl is going to be used up. Kind of like the question was just asked. We've now hit the point where, you know, we've used up all of our HCl, and essentially all we're doing at this point is we're just dropping in there lots and lots of OH minus at this point. This would be -4. By the way, like normal, you got to choose the smaller number. You can't have a negative concentration, so always a smaller number on that change part. That means we got 0 here. We end up with 2 moles of this guy. We end up with 4 moles of this guy. Just like we've been talking about, at this point, you would want to figure out what is the total volume, and you would want to convert these guys back into molarity by dividing by the total volume. And again, if you're not sure sort of what is going on here, you should always look at your ice table. Your ice table does have a lot of information for you and information to help you decide sort of what is going on. So definitely when we look at our ice table, we have sodium hydroxide left over. We also have sodium chloride left over. So from our entire conversation all through this titration curve, we already know this guy is neutral. So even though we got a number, not going to really affect anything. So what are we really left with at this point? We're really left with sodium hydroxide, which is a strong base. So what does that mean? Well, that means that because it's a strong base, that most likely will equal your hydroxide concentration, not your H plus concentration at this point. Again, because you're dropping a ton of OH minus at this point, you were not deterred by that indicator to change color. You just said, I want to keep dropping and see what's going to happen. So what that will get you, again, is not the pH directly, but it will get you to the pOH. And then obviously you could subtract 14 to get yourself to the pH. Any questions on that? And that is the situation that is basically occurring all the way from when you reach that equivalence point and you continue on basically past the equivalence point, again, until you drop basically or stop the titration. And that's why, again, am I really badly scribbled out here? That is why we, again, as we were talking about earlier, you're starting to build up as you're coming through here. Let me actually get a color. Maybe we could see. Let's go with, we'll try yellow. Maybe that'll work. You know, as we're building up through here, again, we're tipping the scales, going more and more OH, less and less H plus, more and more OH, less and less H plus. We're hitting a point here at the equivalence point where they're equal. And now we've tipped the scales going past that equivalence point by dumping more hydroxide in. And that's why we're seeing this big jump in pH, right? Because as the amount of hydroxide goes up, so does the pH, until at some point we're going to hit kind of a maximum amount of hydroxide in that solution. And we will see this leveling off that occurs up on the top part, but definitely it's leveling off, as you can see, very badly drawn across and just scribbling now, that pH in that basic range as we get to the top there. Any questions on any part of that titration curve? What this means is, technically speaking, you should be able to calculate the pH anywhere along that titration curve I choose, or all 500 points along the titration curve, in case I'm mad at you guys, I suppose, but probably not 500 points, I would imagine. But, you know, you should be able to really calculate the pH anywhere along the way. Also, just to let you know, in terms of sort of calculations, you do come across problems where, they're asking you sort of what is the pH at multiple points along the way. So they may say, hey, calculate the pH in this titration after calculate the pH like after 2 milliliters of base is added, and then 4 milliliters of base is added, and then like 10 milliliters of base is added, and so forth. It's important in sort of these type of problems, and usually most titration problems, we think about them as individual processes. So I guess what I'm trying to say is, if you had a problem like this, the first question is really asking, what is the pH after you open it up and add a total of 2 milliliters? The next question is basically asking, after you open it up and you add a total of 4 milliliters, which is basically another 2 milliliters from here. So it's not asking, you don't have to continuously add up all the volumes usually in textbook problems. So you wouldn't be doing like 6 milliliters here, or whatever, 16 here. Again, as we would go from 4 to 10, that's essentially adding another 6 milliliters for a grand total of 10. So in problems, when you're asked that, especially in problems where there's multiple, like, hey, what's the pH at all these different volumes, you don't add all the volumes together. You just think of them as kind of individual problems where you open it up, you stopped at 2, what is the pH? Or you started again, you opened it up, you stopped at a grand total of 4, you opened it up, you stopped at a grand total of 10 being added. Any questions on that there? All right, so why don't you try one just to make sure. So why don't we see here, we'll just make up one. Let's go with let's say we did this titration of 0.1 molar sodium hydroxide with 25 milliliters of 0.1 molar HCl. What is the pH after, we'll go with 32.5 milliliters of sodium hydroxide has been added. All right, so take a minute or two and see what you come up with. I will as well, because I just made it up. So hopefully we'll get anything. So again, this titration is pretty much what we were just talking about. Sodium hydroxide up in the burette, HCl, and here we're adding obviously the sodium hydroxide to the HCl. So take a minute or two, see what you come up with. What is the pH at that point? And I'll do it as well. Not really sure kind of where you are. Hopefully you know where you're at, but if you're not sure where you are in terms of the problems or anything like that, let's just kind of work through sort of the thought process, which is a good idea to do when you're doing these titrations. Clearly we got a titration going on, which means clearly we got a reaction that's happening here. So we definitely have our HCl plus our sodium hydroxide and a little bit of water there, and maybe a little sodium chloride on the back end. Why not? We also know that we're doing a titration, which means obviously we're continuously adding volumes, which has screamed to you, hopefully I better be doing some moles here. So we do want to find the moles of each of these guys. So we'll start with the HCl. Remember, we want to convert it into liters there. So that 25 milliliters would be 0.025 liters. We would use the molarity. So that basically means 0.1 moles per liter of HCl. And that's going to give us the moles of HCl of 0.0025 moles. So again, even if you're not 100% sure what's going on, you hopefully should know that. So that would get you something to fill into the table. We also would do obviously the same thing for our sodium hydroxide, which in this case, converting our 32.5 milliliters into liters and times it by its molarity, which is also 0.1 moles per liter in this case. That gets you 0.00325 moles of our sodium hydroxide, that being our HCl. Gives you again something else to put into your table. This would obviously be 0. First off, any questions on that? So why the ice table is important is, again, if you're not sure where you're at in the titration curve, which is, usually a pretty good thing to kind of have in your head where you're at in the titration curve, because it does help you with the calculation part. Again, we started with HCl in the beaker. We added our sodium hydroxide, and then doing just a quick comparison of these two things, I know that I am after the equivalence point. And the reason I'm after the equivalence point is my moles of sodium hydroxide is greater than my moles of HCl. And that would only occur in this case after the equivalence point, because as we've been talking about, at the equivalence point, those guys should be equal. So A, they're not equal, which means we're not at the equivalence point. And B, what I'm adding is more than what I started with, which tells me I am past the equivalence point. The opposite would be true. If what you're adding is less than what you started with, you would be before the equivalence point. So again, there's a lot of good information that you could kind of get, from this ice table. Any questions on that? That's really important, because that helps us really understand that the change part does have to be, at this point, our limiting reagent, which is the HCl. And again, logic also tells us that we cannot subtract the larger number, otherwise we get a negative number. So we end up with this, and we end up with that. That means at the equivalence point, when we get to the equilibrium part, because we're past the equivalence point, as we would expect, we have now just used up all of our moles of our HCl. We are left with some moles of our sodium hydroxide here. And we're left with some moles of our sodium chloride. Any questions on the ice table, sort of how it looks? All right, at this point, we do want to convert back to molarity here. So we're going to go with our total volume at this point. We started with 25 milliliters. We added like 32.5 milliliters to it. That's something. That's 32.5. That's 57.5 milliliters is our final volume here, our total volume at this point. We would then divide these numbers by 0.0575 liters, as it does need to be converted to liters to make sure that we do end up with molarity at this point. And if we do that, 0.00075 divided by 0.0575, going to give us a molarity of 0.0130 and a molarity of 0.0435 for this guy. Again, if we look at what we have left at this point, we have sodium hydroxide, we have sodium chloride. That is definitely a buffer. No, it's not a buffer. I just want to make sure you're paying attention still, hopefully. Not a buffer, yes. So again, just because you have two numbers, do not use that Henderson-Hasselbalch equation here, because this is not a buffer. So again, that's a super common error people make. As we were talking about earlier, oh, I got a number here, I got a number here. I need two numbers for like the Henderson-Hasselbalch, so that seems like a good idea. It's a bad idea here in this situation. It is the wrong idea. You should not use it. So we want to analyze what we have left. So as we've been talking about, obviously, this still hasn't changed. This is still a neutral salt, which means we don't have to worry about it. What that really means is, as we also talked about before, we pretty much have a strong base left over. And because this is sodium hydroxide, it's a 1-to-1 relationship. That means that is the OH minus concentration. That means we could go into our POH, and we will end up with a POH minus the log of 0.013. We'll call it 1.89 on the POH. and the pH would then be 14 minus our 1.89, and that hits us at a, there we go, like a 12.11 or something like that, I think, which is a basic pH, and it is sort of what we would expect to be happening at this point. Since we're past the equivalence point, we're just dumping in more base at this point. This is exactly what we would sort of expect to happen. Any questions on that calculation? We could kind of see how we did. We were at 32.5, which is here. We ended up at 12.11-ish. So that makes sense. At least we're in the middle there. That's pretty good. Any questions on that calculation or this type of titration? What is going on? Again, you do need to be able to, obviously, as I mentioned, pretty much calculate the pH anywhere along the curve. Any questions on any part of that?
Yeah, I have a question for you. So how did you know that the HCl was a limiting reagent? Was it because it was less than the sodium hydroxide?
Yeah, so essentially that's really why. It's just the very simple answer is we really can't have any negative sort of concentration or moles or anything like that. So when we look at this situation where we're at this point, the sodium hydroxide, which is what we're adding, we actually have a lot more of it than the acid that we started with, the HCl in this case. So that basically turns our sodium hydroxide into that excess reagent. Just by the numbers, it has more. So it's going to be, you got plenty of it. It's not going to be used up because it is a one-to-one relationship between those two things. So it's basically, you know, kind of apples and apples. You need the exact same amount basically, you know, to be equal. So if you have more than one, then you got excess of that and less of the other. And the opposite effect would occur if you did a calculation before the equivalence point. What you would see is this number here, if you were before the equivalence point, would be less than the moles of the HCl that you started with. And that's also, again, how you could use these ice tables to know where you're at in these sort of titration curves by just sort of those two things. You know, if you, whatever you're adding is less than what you started with, you're before the equivalence point. If they're equal to each other, you're at the equivalence point. And then if you're adding, whatever you're adding is more than what you started with, then you're past the equivalence point. So those are the three sort of points that you can kind of look at. But it is as simple as just number wise, you got more of the other than, you know, the first guy.
Okay. And then with sodium chloride, is that one, does that tend to be just a neutral salt overall, or like they just happen to be with our examples?
It does tend, the sodium chloride itself, just by itself, is a neutral salt. So kind of like what we talked about, I think it was in chapter 14 when we talked about hydrolysis and salts. And it's because basically the sodium is from group 1, and anything from group 1 or 2 that's a metal is typically a neutral salt, because really that's where all of our strong bases come from, like sodium hydroxide, potassium hydroxide. And because it really truly came from, as you can even see in this equation, that sodium really did come from sodium hydroxide. And because that sodium hydroxide is a strong base, the relationship is its partner, which would technically be, you know, the sodium on the other side, would be a weak sort of conjugate. So it's basically neutral. And the Cl minus part of it came from our strong acid here. And again, it's that same sort of relationship that because it came from something strong, it's going to be weak and neutral, basically. And basically by weak, we mean it won't react with water and produce anything like hydroxide or H+.
Okay, thank you.
You're welcome. Other questions? Okay. So this is one type of titration, and it's specifically what we talked about here in terms of the calculation part is specifically for this type of titration, which is a strong acid and a strong base titration. Now, things do change when we kind of change up the titration. So let's talk about the next type of titration that we might come across. And this is a titration of a weak acid and a strong base. So for example, here we have something like acetic acid, which is a weak acid, plus some sodium hydroxide, which is a strong base. And again, we do get a reaction. It's going to be a double displacement reaction, really. So we'll get some sodium acetate. And we'll get some water here. And again, the setup here is very similar to the one we just talked about. In the burette that we are adding would be the sodium hydroxide. Down in the beaker or flask would be the acetic acid in this case. So again, we're adding our acetic acid, our sodium hydroxide to our acetic acid in this fashion. We do see a similar sort of S curve, which is typical titration curve that we see. But there are some differences between, say, this titration curve and the one we talked about before. So let's kind of look at the same parts. Let's talk about what happens here at the very beginning, just like we did before we add any sodium hydroxide. So just like before we add any sodium hydroxide. What do we have in that beaker if we want to figure out the pH? Well, what we have in there is acetic acid. And acetic acid, as we've talked about, is a weak acid, which means if I wanted to figure out the pH before I started the titration, it is different than the one we did before. The one we did before was hydrochloric acid, which was a strong acid. This is a weak acid, which means we have to do a Ka problem. So you would need to set up an ice table, which is obviously much different than going right into that pH equation like we did in the last titration. In this case, because we haven't started adding any sodium hydroxide, we could just use the molarity of the acetic acid. These guys would be 0, our initial molarity. The change would be X's. We would have our initial molarity minus X, X, and X. This good guy will go into our Ka. We would solve for X. In this case, X would equal the H plus concentration, and then we could get to the pH at this point. So again, this is a problem we've done before in chapter 14. It's basically a Ka problem. It's obviously much different there than our previous one where we have the strong acid, where you could just kind of go right into the pH equation. So it again going to require some ice table, may require an assumption, may require some quadratic formulas action. Hopefully the assumption will work, but you will have to go through an ice table here because again, we're starting with a weak acid in this case versus a sort of strong acid. And we do sort of see that when we look at the titration curve in terms of just, sort of where we're starting in terms of our initial pH. And that's why when you look at sort of this type of titration, where we're doing a weak acid and strong base titration, we can also see that, we're kind of starting a little bit higher on the pH than we did with our strong acid, which completely breaks apart. Again, because it doesn't completely break apart, it's going to produce maybe a little less H plus. And that's why almost our starting pH is a little bit higher than, again, what we initially started with in that last titration. So as you can see here, this type of titration curve a little bit different to begin with. So it is important to know sort of, what type of titration we're talking about when we do these things. And I see by the time this is probably a good place to lay it up, I think, here for lecture. Any questions on that? All right, we will stop here for lecture now. We will roll into lab at 1-ish. And again, we'll watch the video for experiment 6 so you can finish that up. We'll also talk about experiment 7 as well. So if you haven't done so already, make sure you put here, and I'll see everybody in about 15 minutes or so in lab.